Okay, as people begin to file in, I'll begin my introduction of the first panel of today. So welcome back. We'll now begin our panel entitled Next Generation Technologies for Carbon Capture, Utilization, and Storage, known colloquially as CCUS. Our speakers will address direct air capture, direct ocean capture, techniques for transforming carbon emissions into useful products, and innovative carbon sequestration approaches. Our moderator for the panel this morning is Professor Emily Carter, the Gerhard R. Andlinger Professor in Energy and the Environment at Princeton University, as well as Senior Strategic Advisor and Associate Lab Director at the Department of Energy's Princeton Plasma Physics Lab, or PPPL. She was the founding director of the Andlinger Center and was the director when I was hired about 10 years ago. And she was then afterwards the Dean of the School of Engineering and Applied Sciences, or SEAS, at Princeton. After that, she served as UCLA's Executive Vice Chancellor and Provost and Distinguished Professor of Chemical and Biomolecular Engineering before returning to Princeton and PPPL a few years ago. The author of over 450 publications and patents, she has delivered nearly 600 invited or plenary lectures worldwide, serves on advisory boards spanning a wide range of disciplines. She's the recipient of numerous honors, including election to the U.S. National Academy of Sciences, the American Academy of Arts and Sciences, the U.S. National Academy of Inventors, as well as the U.S. National Academy of Engineering, and the European Academy of Sciences. Please join me in welcoming Emily Carter.
Well, thank you all for being here. It shows how important the topics of today are. I'm going to give a defense here in light of the remarks of the keynote speaker who said that CCUS is not needed. Maybe that was a misinterpretation, but we can talk about it afterward. It's clear that we still need to get carbon dioxide out of the atmosphere given the extreme weather and climate change we're already seeing. So there is definitely a need for the work that you're going to hear about today. We can have more discussion on that later. I would also just like to take one editorial remark to say that I am delighted to see that Rick Andlinger is here, who has been instrumental since the beginning, as has Paul Mader, in how the Andlinger Center has evolved, being parts of the executive committee. Rick is the son of the late Gary Andlinger, who I had the privilege and joy to work with to realize his dream. He would have been delighted to be here to see what his dream of this center has become. So I want Diane to not count any of those remarks as part of my time. Okay? That's got to be said. With that, let me first say that it just provides great joy for me to have twisted the arms of these three terrific individuals who are at the cutting edge of the CCS part of the CCUS. And so I'm going to start by introducing our panelists. Erika Plante, first of all. Erika is co-founder and head of MERV, MRV, for those of you that I believe very strongly that in defining all acronyms one uses. Measurement, reporting, and verification. So she's the head of measurement, reporting, and verification and environmental impact assessment at Equatic. Some of you may have known it in its earlier stage, as I did when it was first formed as Sea Change, but it changed its name in the last year. An ocean carbon removal company that accelerates and amplifies the ocean's natural ability to absorb and permanently store atmospheric carbon. She is also an assistant professor of material science and engineering at the University of California, Davis. She applies her expertise in geochemistry to address many issues in climate sustainability in the built environment. Welcome, Erika.
Thank you.
Our next panelist is Noah McQueen. He is they are the co-founder of and head of research at Heirloom, a direct air capture company with the goal of removing 1 billion tons of CO2 from the atmosphere by 2035. I must say that Heirloom, he's going to talk about this a little bit, is a central partner in one of the recently announced direct air capture hubs. Noah's experience expertise surrounds carbon capture and removal with a focus on direct air capture and carbon mineralization technologies. NOAA's expertise further includes techno-economic analysis and life cycle assessment to evaluate the technical and economic feasibility of carbon removal systems. They hold a PhD in chemical engineering from the University of Pennsylvania and a BS in chemical engineering from the Colorado School of Mines. Thank you so much for being here, Noah. Next, Erika came all the way from Norway to be with us.
Sarah.
Sorry, Sarah. Jumped to the wrong place. Sarah came all the way here from Norway to be with us. She is the research director and chief scientist in computational geosciences at NORCE, an independent research institute in Bergen, Norway. She currently leads the Center for Sustainable Subsurface Resources, a national research center dedicated to providing new subsurface knowledge and digital solutions to reduce Norway's offshore emissions drastically. Norway is really at the cutting edge in terms of the sequestration technologies. I added that, you didn't. You didn't add that. She is an internationally recognized expert in CO2 storage technology with contributions to understanding long-term migration and containment, leakage risk, gigaton scale storage assessment, and storage in depleted petroleum reservoirs. And I must say, I invited her because I heard her speak at an international conference in the spring, and I was really impressed, and I had no idea about this next little bit of the blurb, but it's icing on the cake, which is Sarah holds a PhD in civil and environmental engineering from none other than Princeton University in 2008, a Princeton alum. So with that, let me just set the stage. I've asked each of our panelists, and I will be representing, because I work on carbon utilization, I will be representing the carbon utilization piece. Each of us are going to take 10 minutes to talk about our technologies or our sense of the technologies in the areas of, first, direct ocean capture, direct air capture, and then sequestration and utilization. And then we will open it up for questions. So with that, I'm going to turn it over to Erika.
Thank you so much, Emily. So I have a few slides to describe Equatic, an ocean-based carbon dioxide removal technology. The ocean is Earth's largest CO2 reservoir, and currently it removes about a quarter of our global annual CO2 emissions. Sorry. So it currently removes about a quarter of our global annual CO2 emissions. And there are various technologically enhanced pathways to accelerate this storage. And this includes increasing the growth of marine plants, increasing ocean alkalinity, as well as electrochemical separation of CO2 from seawater, and then followed by direct ocean capture. It is important to consider, though, that this same equilibrium that allows the oceans to absorb CO2 from the atmosphere also implies that the removal of CO2 from the atmosphere would be partially offset by ocean degassing. And there's one model that estimates that, for example, if we have a pulse removal of 100 petagrams of carbon, this will be followed by ocean degassing over a period of 30 years, such that only about a quarter of that CO2 that is initially sequestered is actually permanently removed. And so with this consideration, it's important to think about technologies that also increase the ocean's capacity for storage of CO2. So Equatic is a process that accelerates and amplifies this natural ability of the oceans to absorb CO2 at a gigaton scale while also producing carbon-negative hydrogen. And so this production of alternative fuels like carbon-negative hydrogen, for example, to replace fossil fuels is important. This clean and renewable energy sources because it will help us decarbonize industrial sectors, as well provide electricity and provide alternative fuels for sectors like trucking and aviation. And this Equatic technology, which has been born of about a decade of research at UCLA engineering, is described in this schematic. So we have first the application of electrical current in seawater, and this current then induces chemical reactions that does two things. So one, we have the hydrogen that is freed up from the seawater. This hydrogen can be used to power the plant as an energy source, but also be sold as fuel. And then the other thing that happens is the splitting of the water into two streams. We have an acidic stream and a basic stream. In the basic stream, the calcium ions that is trapped in that seawater reacts with CO2 already dissolved in that seawater to produce calcium carbonates. And also we have the production of magnesium hydroxide in that seawater, and the sequestration of CO2 happens when we bubble that basic stream with air or with a point source of CO2, and this allows the magnesium hydroxide to dissolve and CO2 to dissolve. That traps then the carbon in the form of bicarbonate and carbonate ions. And then meanwhile, in our acidic stream, the acidic stream is then used to dissolve rocks, to release or to replenish the calcium and magnesium, as well as to neutralize that acidity. And in the end, this neutralized seawater is then discharged back into the ocean where the carbon is going to be permanently stored. So because we have here the co-production of hydrogen, this allows us for cost deduction at scale. But also in addition to hydrogen, we also produce oxygen. We also produce calcium carbonate that can be used as green building materials. Another co-product would be the softened water that can be used for desalination. And then also minor metal co-precipitates that's extracted from that seawater. So this Equatic technology is an engineered CDR process that really combines direct ocean removal and direct air removal. So per kilogram, seawater has 2.6 millimoles of dissolved inorganic carbon, 11 millimoles of calcium ions, and 55 millimoles of magnesium ions. The first stage of the process can be considered as direct ocean capture, direct ocean removal, where we have the CO2 that is already dissolved in that water is transformed to a new phase, to a solid phase, to permanently store that CO2 in the form of calcium carbonate solids. And then in the second stage, this is an aerator that is within the battery limit of the plant. So we do this within the plant. There's an additional sequestration of 100 millimoles of CO2 that's then trapped in the form of ions, bicarbonate and carbonate ions. So in total, we sequester 4.6 grams of CO2 per kilogram of seawater that we process. So these two unique pathways, there's two unique forms of carbon, both as solids and as ions, have a stability that exceed 10,000 years. So it's a very durable means of CO2 storage. So where we are now, we are currently operating two fully functional pilots, one in Los Angeles and one in Singapore. Each of these pilots has the capability to remove 100 kilograms of CO2 per day while producing 3.5 kilograms of hydrogen per day. We are also on track to reach commercial scale at 100,000 tons of CO2 per year while producing 3.6 thousand tons of hydrogen. And we recognize that for CDR, for any CDR technology, that cost and scalability are interrelated and really obstacles for deployment of these technologies. But because we have a single process that produces two valuable products, one is the carbon negative hydrogen and the carbon removal credits, then we are able to drastically reduce our cost and increase our scalability in the near term. So our goal is to reach Gen 2 commercial scale of 1 million tons of CO2 per year. That's equivalent to 35,000 tons of hydrogen. At this scale, the hydrogen that is co-produced in the process is sufficient to offset production costs. And then if we multiply this by 1,000 times, then we reach gigaton scale. At this scale, the hydrogen that we produce can fully decarbonize hard-to-abate sectors like steel and cement. So companies like Boeing and Stripe have already recognized the Equatic's impact. And in summary, so we're doing, our vision is to translate science to societal progress, and we do this by developing and operating these technologies that are scalable, that decarbonize today. Thank you.
Thanks.
Awesome. Well, I'm Noah, and I'm going to talk to you a little bit about direct air capture and then the specific company that I work with named Heirloom. So as a little bit of context setting, the world requires permanent carbon removal to stay below 2 degrees Celsius warming. So shown here is from the IPCC AR6 report. see not only requires deep decarbonization of our global society, but also some level of removal. And that really serves two purposes. The first is there's a series of hard-to-abate sectors where it's exceptionally difficult or otherwise unjust to decarbonize. There's also historic emissions. So we've been emitting CO2 at massive rates into our atmosphere since the Industrial Revolution, and we need technologies that can take those historic emissions out of the atmosphere. So before I go too much further, I do want to make a distinction between carbon capture and carbon removal, as they're often conflated. In carbon capture, you're actually avoiding emissions before they reach the atmosphere. So this is similar to putting a sponge on the outlet of a natural gas combined cycle to prevent those CO2 emissions from actually reaching the atmosphere. In a different lens, carbon removal actually creates negative emissions. So instead of going where CO2 is being emitted, you're pulling it directly out of the atmosphere. And this enables us to have, pull CO2 that's either historically been emitted or been emitted more recently out of the atmosphere. Atmosphere is a giant mixing vessel, so it doesn't really care. With that, there's a lot of different ways to do carbon removal. So I'm going to talk specifically about direct air capture, but there are several different approaches, such as afforestation, reforestation, direct ocean capture, as was just discussed, as well as things like carbon mineralization. So in direct air capture, you're moving massive amounts of air over these chemicals that have an affinity for CO2. So that as they move over those chemicals, they bind to that CO2 and you get a CO2 depleted airstream coming through. So when that material becomes saturated with CO2, you can send it into a regeneration process. And in this, you're typically either elevating the temperature, lowering the pressure, or some combination of the two to both recreate that binding material as well as produce a pure stream of CO2 that can be used for CO2 utilization, permanent storage. In particular, Heirloom's process actually merges that process of direct air capture with a process known as carbon mineralization. So in carbon mineralization, you have minerals that naturally react with CO2 in the atmosphere to form stable solids. The biggest challenges with this type of approach is that it's hard to monitor and verify that you've actually pulled CO2 out of the atmosphere since it's an open system. That carbon can go pretty much anywhere, typically into waterways. And the other piece is that it has a large land footprint. So in the Heirloom process, we're actually using a mineral-based material to do direct air capture, which has the benefit of being permanent and additional, meaning you've created a system. It's clearly obvious that you've had a climate intervention. It has clear monitoring, reporting, and verification because you can have a flow meter on the outside of the process to actually see how much CO2 you're capturing, and has several other benefits of both direct air capture and carbon mineralization. So what does this type of a system actually look like? So in Heirloom's process, we start with a mineral, calcium carbonate or limestone. If you're not familiar with calcium carbonate, it's really earth abundant, and it's the primary ingredient in Tums, so safe you can actually consume it. So we start with that carbonate rock, and we send it into an electric reactor. In that reactor, it decomposes into two parts. You get a calcium oxide, and you get CO2. That is then, we partner with a storage facility to permanently store underground. So that calcium oxide is kind of a sponge for CO2. So we hydrate that to calcium hydroxide, and we spread that calcium hydroxide out on trays that are then stacked up in the vertical direction, so increasing the surface area for the CO2 to react with. In nature, this conversion of calcium hydroxide to calcium carbonate occurs over months to years. Heirloom has accelerated that to be a roughly 3-day process. So after 3 days, we saturate this mineral with CO2, and we can cycle it back into that electric reactor to once again use it to capture more CO2. So it's a cyclic process that reuses the mineral. So the other question is, how does this actually scale to gigaton scale direct air capture? So there's 3 real advantages with this technology set that goes back to the pieces around scalability. So the first is the inputs. So limestone is roughly 4% of the Earth's crust, and that really enables us to leverage a highly available material. At 1 billion tons of CO2 removal per year, this process would use less than 0.01% of annual calcium carbonate production, since it's such a heavy input into cement and lime industries internationally. Additionally, this is a really cheap material. It's about $10 to $50 per ton, which is 1,000 times cheaper than other chemicals used for direct air capture processes. The second piece is modularity. When we think about gigaton scale anything, we need to think about supply chains. Modularity enables mass manufacturing. The way we think about this process is our fundamental level of modularity is a tray, and then you have a stack of trays, and then you have a bank of stacks. And all of those should be independently able to be manufactured and kind of just propped up on site. So as little construction on site as possible, which really leads to the complexity of some of these quote unquote mega projects that we build. The more modularity you can have, the more likely on time, low cost construction. And then the final piece here is learning from every ton. So we collect tens of millions of data points every month. The way we control that carbonation reaction is really based on our fundamental understanding of the reaction of CO2 with calcium hydroxide. So the better we refine that, the more finely we can control that. We actually feed that into software and algorithms that we can update in real time on existing hardware. And we've demonstrated this at our pilot facility in Brisbane, California, which can capture at its entirety roughly 100 tons of CO2 per year. Yeah, with that, this really enables the ability to achieve gigaton scale direct air capture, and I'm super excited to talk more about direct air capture in Heirloom.
Thank you.
Good. It's my turn now to talk about storage. I don't know if this is high enough on my... Everybody hear me okay? It's a little bit odd, actually, to be at this conference, which is about next generation technologies, because CO2 storage has been happening and is happening today at industrial scale. For 20 some odd years, there have been 26 projects all around the world, and cumulatively 200 million tons of CO2 has been stored already today. The figure on the left is showing you some of the different types of storage environments that have been tested and piloted, or even industrial scale, for example, off the coast of Norway that Emily alluded to. And the one thing all these projects have in common is that, well, one, they're all very deep, so a kilometer underground, where CO2 is in very dense phase. So not gas phase CO2, very low density, but very high density CO2, 700 to 800, 900 kilograms per cubic meter, still lighter than water or the other fluids that are there. But again, efficient use of the pore space. The last thing they have in common is that they use the natural geology, the physical mechanisms, the natural mechanisms exploit what is already there in nature to capture and trap the CO2 underground. Very similar to the natural oil and gas accumulations, we'll call them natural because they occurred by nature, that have been sitting underground, trapped in and contained over hundreds of millions of years. So we talk about thousands of years containment, 10,000s of years. It is possible to store CO2 in this manner for hundreds of millions of years, if we know where to look. And of course, we have the analogs from oil and gas industry to show us the way. There are, of course, new things that emerge with CO2 storage that the petroleum industry is not used to. First, you have to put fluids into the subsurface. They migrate in different ways. CO2 is not like oil and gas. It can dissolve in the water. And also, there are other aspects like induced seismicity, pressurization, that are unique to CO2 storage, which have been studied now quite extensively for the last 2 decades, and we believe we have quite a lot of knowledge to support a gigaton scale-up. A picture is always better than words, and this is actually showing you CO2 in a tank full of sand. The sand was strategically placed there in order to mimic the real geology. I'll walk you through it in a second, but I just want to acknowledge that the University of Bergen have developed this room scale flow rig. It is approximately 3 meters by 2 meters wide, so it's an enormous, from a lab perspective, piece of equipment. And there CO2, real CO2, can be injected, and you can see what would usually be something that is invisible, except for using geophysical techniques to observe what's happening 1,000 meters underground. We can see it in real time, the different mechanisms that actually occur. So I'll walk you through a little bit what you see here. So right away, you see there are 2 different injection points. And I mentioned before that CO2 is buoyant, which means it will rise unless there is some barrier. And the lighter color sands there are fine-grained sands that have the capillary forces required to enter into those sands is higher than the buoyancy pressure from the CO2. So already we can see that the natural systems have the ability by force balance to contain CO2. And in the subsurface, this 2 or 3 or 4 centimeter gas plume that is, that is accumulated under this seal translates in the real world to 100-meter thick CO2 plumes, bubbles of plumes that can actually be trapped by force balances in the subsurface. So that is, and the other thing that we see here are these fingers that are this is a photo that was taken at about 5 days after the experiment started, and the CO2 is dissolving into the water. I don't remember the numbers, you were using 4 grams per kilogram of water. CO2 dissolves by about 2 to 4% by mass. And when it does so, it actually increases the density of water, and this causes the density instability, and you get convective mixing. And this is extremely unique to CO2 and some other gases, and that draws the CO2 away from this gas accumulation that could be considered a leakage risk, and into deeper into the subsurface. And after you've let the simulation run, or the model run, eventually all of that gas accumulation will have been dissolved. In real time, we can see in the lab over the course of days. In the subsurface, things move more slowly, so it could take years to tens of years to decades to hundreds of years, but the point is that over time that CO2 will equilibrate with its surroundings and be less and less buoyant. We use all this knowledge to inform the models, and a lot of my work has been going, and I know there's a video here, so I don't know if the AV people can start that. And we use that to inform the simulation tools, and we need simulation tools. We can't perform many of these experiments, they're very expensive. And we take all this knowledge and we wrap it into simulators and show that we in fact know enough about these systems to be quite sure about what is happening, even though we cannot directly observe. For example, this fingering would be impossible to observe underground, but we have a good sense that this is actually happening. And this is work done by my group. And this is open source simulation, which is another very key component here to differentiating CO2 storage from the oil and gas industry that has tended to be less and less transparent. We are moving in the opposite direction with CO2 storage, which is good. Let me bring you to Norway. It was mentioned about CO2 storage in Norway has been going on for the last 25 years. Norway is a country, as many of you might or might not know. A lot of water exists in the country and a lot of hydropower. So there's not a lot of emissions, and the business model for Norway really relies on CCS scaling up and building economies of scale around CCS. There's a lot of good mentioning about how to scale up the capture technologies, and how we scale up the storage technologies has to match the ability to scale up on the capture side. Norway sits on, this is showing you a geological map of some of the major basins offshore Norway. Bergen is there on the west coast, that's where I live. Beautiful place everybody should visit. And there's enormous storage resource potential. But the problem is Norway does not have very many emissions. This is showing you a map from, this is from GEUS, which is the geological survey in Denmark from last year or 2 years ago. That shows you the bubbles are the size of the emissions. And Norway has some bubbles, but not very big. Mainly, most of the EU emitters are sitting deep into the continent, where the only options for CO2 storage would be onshore. And that, of course, has not been a very publicly favorable solution. So the idea is to connect those emitters with the offshore storage resources. And this is not just Norway, it's also the UK, the Netherlands, Denmark, are all developing this type of business models to remove the CO2 emissions from deep inside the interior of the EU out to the offshore. Already in Norway, and now similarly in the UK and Denmark and Netherlands, there have been several licensing rounds. This is very familiar to the oil and gas industry. And there are now five licensing rounds, and you can see here highlighted some of the licenses that are already being developed for CO2 storage. And the success of all of this, because it's import and export of climate gases, really depends on a good deal of trust and reliability in building these chains, which are quite extensive and complicated. So the first such chain is already started now. Norway has actually the world's first end-to-end CCS project focused on pure storage. The US, of course, has been storing CO2 for 30, 40 years in the form of CO2 EOR, but this would be the first in saline aquifers, so pure storage, as we would like to call it. Northern Lights is that business model that is building infrastructure, receiving terminal for CO2 coming from the continent. We're starting first with CO2 emitted from a cement plant around the Oslo area, and it's being shipped by barge around the coast of Norway to be permanently stored off the coast, actually about 50 kilometers outside of Bergen. The key here is that they have linked this full chain project only to hard-to-abate industries. But a lot of talk about, do we put CCS on fossil power? All of the first projects now are on process industry, cement, waste to energy, fertilizer, various different types of industries that the processes themselves emit CO2. renewables will not reduce those emissions significantly. So this is part of the first ever, and it's heavily publicly financed. And this is a vast difference to what's going on in the US right now with the IRA. Norway has come out and funded 80% publicly financed, a 25 billion Norwegian kroner project. Compare that with the EV, electric vehicle policies, which have been highly successful. I think Norway is one of the largest per capita owners of Tesla in the world. And that has cost the government 20 billion Norwegian kroner. Just divide by 10, for those of you who want to get it to dollars, in lost tax revenue from those incentives every single year. So this is actually a fairly cheap project compared to the EV. All of it, of course, is needed. It's dimensions such that this can scale up to gigaton within the next 20 years. So the storage facilities onshore can receive much more CO2 than the initial phases of the project. I'll skip ahead. The US model, as I alluded to, for gigaton scale storage permitting, this is showing you the pipeline of permits on the right that are currently under review by the EPA, Class 6 well permits. And it has increased. We're talking about exponential growth. There are now over, 57 storage license applications for Class 6 permits under review. There's actually a bottleneck in the EPA review. They may not have the manpower for that. But in essence, you can see the explosion. And what it means is that there's many different mechanisms in vehicles to get CCS really off the ground. The European model is to fund publicly funded common infrastructure. And the US model is much more decentralized, but both will probably work. So I think I'll stop. I think the discussion will be really interesting. Just want to leave you with the CCS train has left the station. It is going to happen. It is happening. And it's really just a matter, and there are no technical showstoppers, but it's really just a matter of managing a lot of this emerging technical challenges and engineering challenges around clustering and infrastructure and various things. And I would say that CCS pretty much enjoys quite broad bipartisan support, not just in the US, but also across Europe. So that is really comforting, because if it's very partisan, it could be very easily flipped, and that has happened in the past 2 decades. Now we see enjoying bipartisan support for something that not so often happens. Public acceptance could still be something to be aware about, but we can certainly talk about it in a discussion. And I alluded to transparency. That's key to all of this, differentiating CCS from the past sins of the petroleum industry. We have to be extremely transparent about what we're doing. So I'll stop there. Thank you.
Well, thank you, Sarah. I think your point about bipartisan support is an interesting one. It's likely to be true, but the public acceptance piece is something which I think is of concern still. Yeah. Okay. Anyway, so what I'm going to do. Oh, sorry. Being reminded. Okay, what I'm going to do is very briefly tell you, I'm here representing, in fact, I chair for the National Academy's study that is ongoing. It's a 3-year congressionally mandated study on carbon utilization, carbon dioxide utilization, and actually utilization related to coal waste as well. And I'm going to give you just a very brief set of findings associated with our first report. We're in the midst of writing a second, deeper dive. This was a first report done very quickly to inform infrastructure investments in the United States. So first of all, if we think about CO2 utilization, the scope of what we were asked to think about was not things like carbonation of beverages or enhanced oil recovery, which are just physical transformations, but actually to focus on chemical transformations of CO2 into useful products, either from point sources or from the atmosphere or water into marketable products. So one of the important points is that when we think about whether to use CO2 for utilization rather than storage, its impact, its climate impact, will depend on the product lifetime. It'll depend on the CO2 source, and also the emissions from other inputs such as electricity and hydrogen, and how those and what those footprints are with respect to CO2. And so if we think about, for example, we've already heard about mineralization, CO2 plus minerals. making, for example, cement or other building materials in various ways. That can lead, if you form a solid, that can lead to durable carbon storage. And so that's extremely attractive, especially for building materials that are needed on a massive scale. On the other hand, most fuels, well, I would say all fuels and chemicals are going to have lifetimes that are less than 100 years. And so if you think about that, the best you can do is a circular carbon economy in terms of taking CO2, converting it to something which then ultimately will be released back to the atmosphere. So there's an important point about CO2 source and product pairing in order to have sustainable CO2 utilization. In particular, if you have a fossil source, so if you're thinking about the power plants, which Emery Lovins pointed out should be going away, so that won't be a source, but they'll be potentially, they'll be around for quite some time, whether we like it or not. And of course, there's those fossil sources really have to be used in long-lived products in order to be net zero emission compatible. The point is that fossil CO2 to short-lived products, which is the other option, just delays emissions. Okay? They eventually get emitted to the atmosphere. On the other hand, if you have CO2 that is sourced from direct air capture or direct ocean capture, like we heard, or from biogenic CO2 sources like ethanol plants, then you could imagine making both short-lived or long-lived products. And if you make long-lived products, you are really going net negative, which we will need to do for a while. But if we make short-lived products, at least we are net zero compatible. And so fuels and chemicals in the future, if we're going to make any of them from CO2, and that's still a big if, must come from these other sources, not fossil sources, direct air capture, direct ocean capture, or biogenic CO2. So one needs to do a real life cycle analysis to make sure, in addition to techno-economic analysis, to make sure that one would actually build out some CO2 utilization industry. Okay, I'm not going to go through all of this. This is just to point out the complexity of the problem of the infrastructure needs for CO2 utilization. It involves the same infrastructure needs associated with CCS that we've already talked about in terms of capture. We didn't really talk about purification, but those are big issues as well as how one transport. Sarah mentioned transporting by barge. The cheapest mode is pipelines, but building out those pipelines is, there are many things we can talk about with respect to that. Purification at the end, it's much more likely that what's going to happen in terms of any CO2 utilization is going to piggyback on CCS projects, I think, or very, very likely. And then there are many different pathways for CO2 utilization. And then ultimately, if you've made something, you have to transport that product, and you have to weigh which products, whether it's better to transport the CO2 or transport the product in terms of whether you decide to do centralized or distributed CO2 utilization. And so one of the things that the committee came to is people should recognize the opportunities for co-location to minimize transport. Instead of having to build out a large pipeline network. The US has 5,000 miles of CO2 pipelines right now, but it's basically for enhanced oil recovery right now. So it's in only one, and so they're not located essentially where one could imagine both the sources of CO2 as well as the utilization that one could envision. So it's very important to be thinking about that and to recognize that if you think about that co-location, you could imagine, for example, building materials, marketing near existing point sources and product uses, so near cities. And otherwise, for example, direct air capture facility sited already next to existing chemical manufacturing infrastructure would make a lot of sense. This is a way to eliminate the pipeline need. And so the committee found, for example, in terms of near-term opportunities for investment, to focus on potentially sustainable aviation fuels using as a CO2 source, for example, ethanol plants that generate CO2, and bringing in clean hydrogen and clean electricity. So that some of that work is already going on. There are companies that are engaged in that kind of work. And then there are a lot of companies that are engaged in using sort of any source of CO2 plus minerals and we've heard a little bit of that here today already, to create building materials. So that's sort of the low-hanging fruit over the next decade. In addition, so this is the issue of piggybacking. You see the mention of geologic sequestration, essentially utilizing CO2, bringing again the co-location, the idea of having industrial clusters. This is a big topic and is being realized in the EU already, which is to recognize we should take advantage of the fact that there's already an infrastructure for chemical transformations, and think about essentially piggybacking off of whatever is built for CCS to have it be co-located near this kind of chemical infrastructure, and then be able to take both fossil sources to make long-lived products, as well as direct air capture, direct ocean capture, biogenic sources to make both long-lived and short-lived products. So with that, I actually saved us a little bit of time, and I'm happy to open it up for questions, or I will also, I also have my own questions for the panel as well, and you can also ask questions of me. So thank you. Okay, I see, maybe we can start in the front here for a moment, or, no, but we want to make sure that people can hear. Here you go. And please identify yourself. It's a best practice to identify who you are and who
I'm
you represent.
Jean Fox, an adjunct at Rutgers and at Columbia SIPA, but a regulator for my whole career, utility and environmental. My question is specifically, and I'm doing a class on this at Columbia in the spring, not just this, with sequestration, which Granger Morgan from Carnegie Mellon says you use sequestration and not storage.
Well, yeah.
But
It's
anyhow,
a European thing. But
he got all over me.
blame it on Europe.
But anyhow, the issue I ask is, for instance, USGS or EPA, they regulate this for the US, and it doesn't seem like they have standards or regulations as to where you can put it and where you can't put it underground. For instance, would you want to put it in California where there are earthquakes? So I just wanted to know about that and leakage and how is that handled technically when these are cited.
Okay. No, I mean, regulatory agencies aren't in the business of telling companies where to go discover resources, right? I mean, I think the companies have to find those resources. We do know oil and gas exist in accumulations in California, so we know that it is possible to store buoyant gases underground for hundreds of millions of years in seismically active areas. And there's seismically active areas also in southern Europe. So, I mean, there's a good understanding of how to avoid the worst of the seismic activity and move your way upwards a little bit farther away. So I think it's a lot of good understanding underpins these decisions about where to put CO2 storage. But I don't think it's the regulatory agency's job to, what they do is they're storage atlases. In Norway, it's the same regulatory agency that actually produces atlases that show, okay, here are some of the potentials, but they're very, very rough numbers, and it's up to the companies to refine those numbers into commercial reality. So I don't know if I answered your question, but it's oh yeah, and about the leakage. Yeah, I didn't really allude to leakage at all here. It is possible, of course, it can never rule out leakage. These are natural systems that are imperfect in their own way, and of course, our knowledge of the subsurface is not perfect. But I would, from the estimates and the work that's been done, and also the analogs that we have for CO2 is leaking from natural systems all over the world, it's hard to say that it would be of any consequence from either a climate perspective, environmental perspective, or human health and public safety perspective. But you can't rule it out, and that's the kind of about the transparency part. I think if anybody stands up here and says it will never leak, they're either lying or they're ignorant. I mean, you can't say it can't, it won't. But that's a really important part about being transparent, is to say it might, but we can manage it, we can monitor, and we can identify more serious anomalies. And this has happened already. In the 26 years of CO2 storage, there have been anomalies that have been managed, and it was never any threat to environment, human, public health, or safety. So it's like any industrial engineering activity, there are some risks, but as long as they're manageable, then we should be able to, as a society, accept them. So
I
I hope
think-
that answers your question.
I think the issue, that was great. I think the issue is more with respect to, and again, this gets to the discussion about public acceptance, which I think is really important. You know, EU has already done the experiment. They're not going to first order, have injection underground. No. There is some discussion, I guess, in Switzerland of doing something soon, but you know, who knows? But, and it's because people are concerned, right? And offshore, it seems much safer. And so that decision has been made in the EU. That conversation is still going on in the US as to what will happen. But I think the issue of transparency and understanding of risk will be really important and early community engagement to discuss how it would be managed if there and monitored to mitigate against any leakage.
Yeah, exactly.
Yeah, because people, the public, at least in this country, don't trust industry because they polluted everything.
Right.
They more trust the regulator, the environmental regulator, or the USGS, than they do the industry.
Right.
In the back. Wait for the microphone and please introduce yourself.
Thanks. Hi, my name is Emmett. I'm an undergraduate at
Okay.
Princeton. Is Heirloom's technology used for carbon capture rather than removal? And if so, in what proportion?
No, it's used solely for removal. Yeah.
Okay. Right there too, might as well.
Hi, I'm Edmund Downey. I'm a third-year PhD student in the School of Public Policy. I wanted to ask Sarah specifically about transport and the relative sort of competitiveness position of Norway compared to other actors in the North Sea area, UK, Netherlands, Denmark. How big a sort of share of the overall process costs is transport, and how does that affect, from a proximity standpoint, how do you guys compete against some of these, like maybe Danish sources that are closer to German sources or something like that?
No, it's a very good point. Yeah, it's, let's say you can envision this being a very competitive market where the cost of transport would be the deciding factor. But actually, once you put it into a tanker, the distance the tanker sails is it's not the biggest factor. It's getting it onto the tanker and offloading the tanker and all the infrastructure around. In fact, some people are worried that Iceland, which is even farther away, nobody has mentioned Iceland at all. Iceland has a very innovative approach to carbon sequestration. I will use that for this crowd, which is direct. It's carbon mineralization in situ, and they inject carbonated water. Very cheap. They have abundant basalt, which are volcanic rocks that react within days and months and permanently sequester that in minerals underground. And they can probably even outcompete what's happening in Norway, even though they're farther away. So transport is, I don't remember all the numbers, but it's on the order of 10% to whatever. Storage is also around 10 to something percent. All the cost is in the capture. Because it's an energy intensive process.
Well,
So-
some of them are energy intensive.
Yeah.
I mean, they're all, but to varying degrees. The early ones were
Yeah.
very energy intensive, and I think that's
Right.
getting better.
But it costs energy to do this.
Yeah.
So proximity is not the deciding factor here. It's how cheaply can you get it under the ground.
Okay.
Hi, I'm Sue Dorward. I am a Master's of Carbon Management student at Columbia, finishing up this semester, and Jim Price over there installed my heat pumps, so I was happy to see him. I'm also the sustainability coordinator at Raritan Valley Community College. So I have a question for Noah. I love that you guys got the DOE awards for the DAG hubs. That's a huge step for a startup company. I'm wondering what challenges you face as you look to move those projects forward, and also speaking to the energy usage for your regeneration with the heat, how you're addressing that. Thanks.
Yeah, I'll start with challenges in scaling the technology up. So, we did recently receive a Direct Air Capture Hub Award in collaboration with Battelle and Climeworks, another direct air capture company that uses solid sorbent engineered materials to remove CO2 from the atmosphere. In that, we've actually, we're in southeast Louisiana, which is a part of Louisiana that has been historically devastated by industrial activity. So one of the biggest challenges actually is going into the community and trying to educate on what we're going to do and gain public buy-in and acceptance. And it's a really critical piece of any type of project development. Ideally, you're going in years before the project has even begun engineering just to make sure and engage with that community. Community benefits agreements are something that we are working with communities to develop. So what do those communities actually want to see from technologies, from companies? And oftentimes it has nothing to do with the technology. It's access to healthcare or food security. And how can the company coming into their communities actually provide them with that level of security? So oftentimes the challenges being faced in this regard are not necessarily related to the technology itself. From the other part of your question around our energy consumption, so we've designed a system that runs entirely on electricity. As we've stated, capture of CO2 is an energy-intensive process. It becomes more energy-intensive the more dilute the CO2 is in your stream. So in the air, 410 parts per million, you're talking somewhere between 5 and 10 gigajoules per ton of CO2 that you remove from the atmosphere. So for 1 million tons of CO2 removal, you're talking somewhere between 2 and 300 megawatts of energy generation required for that level of removal. So I won't share our numbers exactly, but that's ballpark for direct air capture more broadly.
My question, I'm Mark Martirez from Princeton Plasma Physics Laboratory. My question is for Erika. So the knee-jerk criticism about electrochemical CO2 mineralization is, of course, what are you going to do with the acid stream? And, of course, your company uses calcium and magnesium silicates, from what I understand. So the reaction is the mining of those minerals going to be sustainable? And is there going to be enough to actually, for you to achieve the gigaton scale that you're proposing?
Mm-hmm. Yeah. I think that's the advantage of this technology. It's scalable because we need seawater, we need rocks, and we need renewable energy source. So with rocks, which is your question, there are enough calcium silicates, magnesium silicates to neutralize our acid stream. And yes, we need to be strategic on these sources. If we could utilize fine tailings, for example, that's already ground, there's energy that's required to grind these rocks so they can be more reactive. So we can co-locate, find locations where all of these resources are in one place, and that would be our best bet.
Right here. Or wherever.
Thanks so much. I'm Elke Weber. I'm a professor here in the Andlinger Center and also in public policy and psychology. And I want to bring the discussion back to the public acceptance that Emily already raised a few times. At this point, the American public and also in Europe don't know very much about carbon capture and sequestration. They don't have strong opinions. And it's a real opportunity to shape public perception rather than bemoan it after the fact when it's too late, like we did with nuclear power and other technologies. So maybe all of you could say a little bit about what kind of initiatives maybe are in place, what kind of initiatives ought to be in place, and also maybe to guard against political polarization, because even though it's bipartisan at this point, that is no guarantee for the future.
Who would like to speak to that first?
I mean, I'm happy to take a shot. We actually just released an opinion editorial on high road carbon removal and kind of what it means to do this responsibly. So I think the first step is that there needs to be a dialogue between not only technology developers, but also policy governments, and that needs to happen at a federal, state, and local level. The thing, in this kind of high roads carbon removal principles, we have things like, we will not use any of our CO2 molecules for enhanced oil recovery, which is actually injecting CO2 in the subsurface to recover more oil that would otherwise be unrecoverable. So I think we really need to start some of those conversations about what does it look like to responsibly deploy these technologies and what standards do we hold technologies developers to. So additionally we have transparent monitoring, reporting, and verification as a tool for justice. So ensuring that we're not only being transparent with regulators, but also with communities. This is what we're going to be doing. This is how we're going to do it. And getting feedback from those communities as well. It needs to be a two-way conversation, not only on the monitoring, reporting, and verification, but also on the community benefits agreements. And then, the final thing is working either with union labor or otherwise to make sure that you are providing quality jobs, quality high-paying jobs in the region that you're actually deploying. So, that's kind of the framework that we laid out, but we really want to start a conversation more broadly. And that needs to extend beyond just the technology developers and individual communities, but also into a framework for how we approach that more broadly.
That's great. I would just say that in the report that I alluded to, we talked a lot about the need for this early engagement with the community and basically sitting, not going in with the attitude that you're there to educate them because you're the expert, but in fact going in to understand their experience, their concerns, and be able to sit down and talk about how, and their fears, right? To be able to address those concerns and fears and to talk about how it is possible to address them and to recognize that that it doesn't mean that every project will go forward, but to put in that early investment long before you're doing it and build trust and have essentially identify people within the community who can help essentially be a translator, right? And a go-between in terms of making sure that there's a trusted person that they're hearing from who also has gained the trust of the developer.
Yeah. I'll add to this discussion. I showed this picture of this experiment, and in fact, the University of Bergen has now built a mobile unit for this, and they go around to all manner of places and have visited actually Berlin recently. And I think a part of it is just showing people what this is. I mean, for CO2 storage, it's 1,000 meters underground. Even scientists, I looked at those pictures the first time, it's like, oh, wow, right? You start to get a grip of what this really means. And people are, smart enough to, once you explain some of the physics and the science with pictures and to see, things happening in real time. There was at the Museum of Bergen, it was part of a big exhibition about porous media science in general, how important that is for our world, not just subsurface CO2 storage, but also medical science and all manner of things where porous media is intricate to understanding porous media is really important. Schools, getting kids interested in STEM, and showing them that there are jobs here. It doesn't have to be in the oil and gas industry. It's a very similar science behind all of it, and they can take their competence and their education and go into CO2 storage, underground hydrogen storage, energy storage, compressed air. I mean, you name it. There's all manner of things that you can use these. So the more we, up and down the society, bring the message about, what is really happening and what the physics behind it, I think also helps build comfort level that this isn't some off the, out of the blue, where do we come with this from? So it's an important part of the communication. And I would say scientists, generally speaking, are poor communicators. So it's also on us to understand how to communicate to different audiences.
Yep.
I'd like to augment this very useful information by getting confused on a higher level about economics. What these efforts have to compete with, in some sense, is efficient use, which is cheaper than buying the fuel, renewable supply, which is generally cheaper than buying the fuel, and of course some of what you're describing is particularly challenging because it's kind of picking a fight with entropy. It's like unpeeing the swimming pool. But what could change that is if the recovered carbon can create exceptional value that more than pays for capturing it, in competition, of course, with natural systems, which already produce value and are designed to in a self-perpetuating way from capturing carbon. Mm-hmm. So has somebody published, perhaps in your committee, a kind of supply curve of quantities and values for uses to which captured carbon could be put, so that we can look at the net value of doing what many of you are describing and see whether there's some hidden gold there.
Yeah, so there have been various papers that have looked at techno-economic analysis of different technologies producing different products. Our committee also spoke to that, and we'll speak to that in this next report in more depth. I think, a good example could be, because you're absolutely right. I mean, one of the things that one has to be concerned about is, obviously, we're made of carbon and water to first order, okay? And so and food is carbon. And so carbon, this concept of decarbonization drives me crazy. It's not, we're not going to decarbonize our world, otherwise we'll all be dead. But the point is that it's the question of where does the carbon come from? And so one has to ask the question, is it best to come from biomass? Is it best to come from recycled plastics? Is it, there's lots, as opposed to carbon dioxide or from coal waste or whatever. Because carbon dioxide is, down here in energy, and anything you do is going to cost energy to make it better. So it has to be something that you clearly see that there is a value to make it worthwhile. So one area that I particularly think, so you either do something that you make very cheaply, and it's just needed in mass quantities, which is concrete, potentially, or you make carbon composites. You make carbon fibers, and you make carbon composites, and you use those as they already are being used for fuselages of airplanes. You use them, as you showed, for the BMW and for other vehicles. And you could use them to build buildings, right? You could do many things, right? Okay, yeah, right? Okay, so you get the point. So carbon composites, and right now, they have tremendous value. So to me, in terms of, I think one should be focused very heavily on long-term durable storage and utilization together, so solids, like concrete, like carbon composites. These are things that, to me, make the most sense. Even though concrete is dirt cheap, because of its massive use, it could be possible for it to be a path forward. So the interesting thing about those two products, right? I'm a chemist by training. One of them is oxidizing carbon dioxide, and the other is reducing it, completely. So it's anyway. I think that's where we likely have to head. Other questions?
I was just going to add to that.
Okay, go ahead.
Yeah, no, I was going to say already in Norway we see a little of this sprouting up of small industry around. But we have to remember that CCS, in the end of the day, is a waste management industry. We have to get rid of it.
Yeah.
We can use it. It's nice to build up some green jobs around these infrastructure projects that we have. But it's a waste management industry, and a low margin one at that.
Yeah, it's really important to frame it that way, because we worry about waste management in other parts, and it's a social good.
Yeah.
Okay, and while I agree with you that eventually we will be decarbonized, we will be defossilized, let's say that, the fact is we have to pay for the sins of the past. And so at the very least, we need this to pay for the sins of the past, in my opinion. Okay, yes?
Yeah, Paul, I'm a student at NYU. And I had a question around this whole creating value from a waste management, a low margin waste management. And is there any way we could create a social positive encouragement to use it, like a certified carbon captured created products,
It's already happening.
Yeah.
Oh.
Oh yeah, there are people, I was asked my opinion, apparently there are CO2 captured vodka is on the market, okay, for example. They market it that way.
But is there a way that we could make it formalized like a USDA certified organic situation?
Yeah.
They are looking at government procurement of low carbon materials too. So concrete and cement is one. There's also now a government procurement call for CO2 removal credits. So the government actually taking that first step in catalyzing the market. It's really interesting. Yeah.
But the problem is a lot of these products are very low TRL. right? So, I mean, it's going to be decades before they blossom and bloom. But we still have the sins of our past that we need to get rid of very soon. So I think the carbon utilization market will build over time.
Right.
But we shouldn't wait for that.
No, we can't wait for it.
Can't
But
wait
we
for
have
that.
to build out the infrastructure for CCS in anticipation with the flexibility to build in the possibility of CO2 utilization.
Agreed.
That's all. Because what I would say, too, is that it is not obvious, unless we focus only on offshore, that there could be an outcome, which would be not good, but that it's happened in the EU, that the societal acceptance prevents us from doing CCS, and we may have to at least get there, and through this societal acceptance, perhaps actually CU can help with that societal acceptance too. Or it may end up being one of the only options. Okay.
Elie Bouzid, professor in civil and environmental engineering. Hi. So the panel and the morning talk, would make one very optimistic about the ability of the global north and China and India to decarbonize and sequester carbon. But the biggest demographic boom is in Africa and other countries in the global south. And if oil gets very cheap, the economic incentive in the global south might be very different from what we have in the global north. So I guess my concrete question for the panel is how translatable and applicable would your technology be in Africa? What happens when oil becomes very cheap? And any thoughts, any projects along these lines anywhere in Africa?
I don't know very much about what's happening in Africa, but I would say that from the storage side, there's a tremendous amount of expertise that's needed, and that usually it isn't so available in Africa right now. So I would say that the best bet for Africa would be to look at carbon neutrality as the means to grow their economy and decouple it from growth in carbon emissions at the same time, right? I think that's my non-expert opinion on the African economy and how to get them there. But I think direct air capture is a really good way to do that, because you can create with energy, of course, synthetic fuels, so they don't have to replace all of their oil-based infrastructure. You can create those synthetic fuels with the stranded solar assets that are in Africa, or wind for that matter, and help them decouple their transportation emissions from carbon emissions, or transportation needs from carbon emissions.
Maybe adding on to some of that, there are some organizations in Africa pulling together technology providers, energy resources, and geologic storage experts. Specifically, in Kenya, they have widely, vast solar potential, opportunity for carbon mineralization, so injecting CO2 underground where it forms carbonates as a form of permanent storage, and then you can put a direct air capture process right there, because direct air capture can pretty much go anywhere, but you want it co-located to storage. So there's a lot of opportunities in the global south to also use these technologies as an economic catalyst in those regions, and have the majority of emissions came from the global north, have the global north actually invest in those technologies in the global south, create jobs, and help elevate standards of living. That's just one project that I know of. I know there's also a mineralization company that I think was founded out of Colombia that is currently exploring kind of the Kenya region for in situ geologic storage.
Yeah. In Oman there's a number of places in Africa that are rich in the basalts that allow this kind of storage. So, and I think from the previous talk that we heard from Amory Lovins, the hope is that Africa doesn't go the oil and gas route more, but in fact leapfrogs to wind and solar, but especially solar. So, yes.
Yes, just a quick comment on the question about the use of CO2. The Australian government is really investing quite a bit in this. They've just established an ARC Center of Excellence for next 7 years on what is called GET CO2, green electrochemical transformation of carbon dioxide. A lot of it is going to go towards research on methanol and ammonia production and so on. But I'm wondering, in the National Academy's work, Is that something also, as you rightly said, and my first training is in chemistry, too, I'm a professor at the University of Delaware, but basically, you have the entropy challenge, but is that something the academy is also looking at, the electrochemical transformation of CO2 into methanol? And
Yeah, so many different processes, photoelectrochemical, photochemical, solar thermochemical, electrochemical, plasma-based, you name it, and thermochemical with for example, with carbon capture. There's a question in the back. So yes.
Jeff Goldmere from General Electric. Great panel. Thank you all very much. I just want to pass a comment first to the individual who asked about seismic activity and implications for sequestration storage. It's a great study done by the global CCS Institute, so the Global Carbon Capture and Storage Institute. They were actually doing a CO2 injection test in Japan during the time of the Fukushima earthquake and have detailed information about the implications for their pilot. I'm happy to help connect you afterwards. For the panel, as we talk about the use of carbon and the concept of whether you're using DAC for removal or you're talking about recycling, there was an interesting study result coming out of Columbia where they talked about, for example, in the aviation industry, their view was don't go the route of sustainable aviation fuel. The cost and implications of that are larger. Just do DAC. Keep using Jet A as you do today, and it's actually better just to use DAC instead versus DAC to get the carbon to make sustainable aviation fuel. If you take that as a framework, and the energy costs, where do you think, if we're talking about using DAC and these technologies, where should we be applying them, and what are the places that we should just say, for the time being, it's a lower priority?
Well, one thing I will say, I heard a talk by someone from Boeing and what their plans are. And what I would say is, first of all, it depends on what, I think it was alluded to before that maybe it was in Amory's talk as well, that at least up to a certain size of airplane, you're not going to need jet fuel in the future. I mean, there'll be some electrified vehicles for small craft, and then the thought is to move to hydrogen, but you're going to need jet fuel presumably for 787s, I would venture to say. So then the question is, so I haven't seen the study that you talked about, so I don't know. I'm curious to know, and haven't done the math. I don't know if you've done the math, Noah, about this with respect to DAC, DAC plus fossil versus making sustainable aviation fuels. It also is going to depend on where those aviation fuels come from. There are multiple sources of them. So the question is, does it come from, and which process it involves in terms of taking the CO2 to the fuel? Do you have something else you want to add?
Yeah, maybe just at a higher level. The oil we extract is always more dense than the CO2 we re-inject, so we can't continue extracting. We have to sunset all types of oil and gas extraction. Otherwise, we won't run out of places to put it, but it's going to require it already is going to require a massive amount of infrastructure, and to use this as a tool to continue emissions is something that I just don't think the technology should be used for.
Okay.
On that note, I apologize. The panel is over at noon, which it is noon by my watch, and I would like to just thank Emily Carter as moderator and all of the panelists for the first panel. And now for some public service announcements. Don't stand up just yet. Lunch will be held now, as soon as you can get there, at the Frick Chemistry Atrium. And that is about a 10-minute walk. It is mostly downhill on this way. And that will be until 2 p.m. There will be a poster session that will start in about 20 to 40 minutes. And that will be at the same time and same place as lunch. And so you can feel free to and are welcome to and encouraged to visit as many posters as you can, many of which are fascinating, 2 of which come from my group, actually. So just a plug for that. And there will also be shuttle buses for those that would prefer or would require the use of a shuttle bus. And there are the fleet of electric buses that we have here on campus. And so you don't have to feel bad about riding the bus if you just don't feel like walking. I will be walking. And there will be others walking from the staff here that you can follow, and they'll have, I think, flags to help direct your attention in the right direction. Thank you.